All right, everybody, I think I'm gonna go ahead and get started here. Welcome to Thursday. It's so much nicer outside finally. The nice cool weather is refreshing, at least for me. I'm enjoying it a lot. Hope that you guys are too. Hopefully it'll stay this way for a while. Got a couple of quick announcements, but not a whole lot. We're gonna jump right in pretty quickly. First of all, do not forget, please, that there is a homework assignment that's due tonight, and that would be homework number 4. I've left room during the break today. If you have been working on that assignment and you want to ask me anything about any of those problems, you can put some problem numbers on the board on the side over there during our break. And then in the second part of the class, I'll try to save a little time for anything that's there. It's a pretty quick assignment though. Overall, I don't think it should be too bad if you're still working on it. Hopefully not too big of a deal. You'll just need to turn that in by midnight tonight, basically. And I have a lot of office hours as well this evening. Some of you, I hope will still take advantage of the chance to stop by and just introduce yourself if you haven't done that yet. Today's another great day to do that. Because I'll be around all day pretty much. Your next assignment after the one due tonight was supposed to be due on Sunday. I'm not sure I'm going to actually be able to have my Sunday office hours this week. I'm planning to go hiking on Sunday and I just don't know if I'm gonna be back in time. So what I decided to do, because the next assignment, which is the homework number 5, it's got a lot to it. I decided to just go ahead and push that to next Tuesday, but there was already an assignment due on Tuesday next week. So I've actually just merged them together. So 5 and 6 will both be due on Tuesday. That'll be great for us to take questions in class on Tuesday about both of those assignments. Number 6 is a pretty short one, and we'll have all of that material covered by today. So let's just do both of them for Tuesday and kind of handle it that way. I think that would be the best. So that's just a slight change. I did update the due dates in Canvas for you, so you can see that there. Hopefully that'll all make good sense to you. Okay, that's it for my announcements, pretty much. The homework assignments is all I really needed to say anything about. Anybody have any questions? Yes.
Where are you going hiking?
I might I'll send you something to watch over the weekend about what I'm gonna do. I might go climb the 14er in the Sierra Nevadas that's next to Mount Whitney, which is the highest mountain in California. So I've climbed half of California's 14,000-foot mountains, but I've kind of been in a lull lately, and this might be a good weekend to do it. You have to have a permit. I did get a permit, so that's step 1. Then I just have to wake up and decide I'm actually going to go do it. I could change my mind because it's hard to find the motivation sometimes, but I'm feeling pretty good that I might go do that. So we'll see. Good question.
You checked the weather, right? So
I
it's
did
not
check the
like
weather.
Arizona.
Huh?
So it's not like another Arizona.
At 14,000 feet, it's not going to be that hot.
I know I meant the incident where you got your teeth.
Oh, that whole thing, yes. Oh, you remember that from last year?
Yeah.
Yeah, oh yeah. No, hopefully that won't be a problem. But this one is a knife edge ridge main thing I'm just checking is the wind. Because if it's too windy, I'm not going. Anyhow, enough about all of my crazy adventures. What I think I'm gonna do here is go through a quick recap of where we left off on Tuesday. And then we're gonna finish chapter 2 today. Okay, we'll finish chapter 2 today. So, I had talked about this idea of an inverse of a matrix. Okay, so we cannot do division. We can't divide by a matrix, but this idea of calculating an inverse for a matrix is going to be kind of a next best thing. It's like a analogous thing that we can sometimes do. Now, in order to be able to even talk about this, notice that the matrix that I start off with has to be square size, right? N by N, square size matrix. So that's important. If we have a square matrix, then if there is another matrix of the same square size, I'll call it B, such that when I multiply A and B together, by the way, this is if, right? Not saying you can always do this, but if there is another matrix B such that A times B is the identity matrix, whichever order you multiply them in, then we are going to call B an inverse of A. Okay, so a matrix will have an inverse if you can find something to multiply it by that gives you the identity matrix. Let me just remind you here, guys, the identity matrix, that's I sub n. It's a diagonal matrix that has ones on the main diagonal and zeros everywhere else, right? Okay, and the idea of this matrix is that it kind of behaves the same way that the number 1 behaves. When you multiply by 1, nothing happens, right? If you multiply by the identity matrix, nothing happens. Okay, so that's kind of the way to think about that. Now, again, this is a big if. Not every matrix is going to have an inverse. So I want to be really clear that if B is an inverse of A, that's kind of a special situation if that happens. And we're going to say that A is invertible. Okay, so we'll call a matrix invertible if there's another matrix that you can multiply it by to sort of cancel out to the identity matrix. That's the definition here. It's a little bit abstract, but we're going to do examples, of course, in a moment. But that's the idea here. Now, there's lots of questions that you're probably having, like, how do I know if my matrix is going to have an inverse? If it has an inverse, how do I find it, right? And who cares if a matrix has an inverse, right? All these are good questions about inverses that we need to kind of address here. So we're going to do that. The first question, though, I actually want to take care of. I have a very specific order that I'm doing this in right now. This is the first question I'd actually like to answer. If a matrix has an inverse, could it potentially have 2 inverses? Could it actually have 2 inverses? And I want to answer this question first, because if the answer is no, then that will mean that the invertible matrix A has a unique inverse, and then we can kind of use a better notation for it than just capital B. And it turns out, guys, that the answer here is in fact no. If a matrix has an inverse, it will only have 1 inverse. Okay, so that's kind of good. So I'll just say here, an inverse must be unique. Unique just means there's only one of them, right? There's only one of them. So I'd like to actually prove that. I would actually like to, part of what we're going to do with the linear algebra is get a little taste of theoretical math, right? It's not like calculus where you're just crunching numbers all the time and using formulas. There's a little bit of theoretical maturity that a mathematician can develop. And one of the main things that is involved in that is the idea of proof. So I am going to actually write you a proof of this, and I believe that this is actually in homework number 6. So I'm kind of going to be doing one of your homework problems for you right here. Okay, so you definitely take notes on this, then you can just refer back to this later when you're doing the homework for next week. Does anybody have an idea how I might, just conceptually, how would I try to show that something is unique? That there can't be 2 of them? Yeah, Blake? Exactly. We could say, suppose that there are 2 inverses for A, and then we could show that, no, there's not really 2 inverses for A. They actually have to be the same. That's exactly what we're going to do, okay? So what we're going to do is, let's assume that B and C are inverses of A. Let's suppose that A has 2 inverses. I'll call them B and C. And then, of course, what we're going to do, hopefully, is show that B is actually equal to C, right? It's not really 2 inverses. These are just the same thing, okay? So to do this, let's just write down what this means. So this is like a little paragraph, guys, giving a little explanation for this little fact right here. So this means that, A times B is equal to the identity matrix, which is equal to B times A. And also A times C is equal to the identity matrix, which is equal to C times A, right? We would have all of those equations because both B and C are inverses of A. Suppose we could have that. Okay, and now what I'm gonna do, guys, what I'm gonna do is I'm gonna start here with B, and this is the part you'll be writing up on your homework for next week. I'm gonna start with B, and I'm gonna try to eventually get over here to C. All right, let's see if I can fill in some steps here. If I start with B, I think you guys would all agree that I can multiply it by the identity matrix. Remember, that's like multiplying by 1. So it does nothing, doesn't really affect the product at all. So if you took any matrix times this identity matrix, it's just going to give you that same matrix back again. Okay. Now, what I'm going to do here is I'm going to take out the identity matrix that I just put in and replace it with A times C. So remember that A times C is equal to the identity matrix, so I can just slip that in there. We learned last week that with matrix multiplication, if I'm multiplying matrices together, you can change the parentheses, no problem. It doesn't change the answer. So I'm actually going to do that here. I'm going to put the parentheses over with the BA. Notice I'm not switching the order of anything. B comes first, then A, and then C. And I'm leaving it in that order. But I parenthesized it differently here. And what does B times A equal to? The identity matrix again, right? That's still the identity matrix. So we get the identity matrix times C. And look, you can tell I've done this a few times. I have exactly the right amount of space there. That comes out exactly to be equal to C, right? So if you take the identity matrix times anything, it just leaves it alone. So that's it. So B is equal to C. This is this one line right here. I believe that this is section 2.6, number 39 from the homework. There's a question that basically asks you to write that up. And so that's on your assignment. And all you have to do is write that down. It's very short and sweet, but it is abstract. I will give you that. It's definitely abstract. Okay, so inverses are unique. If you imagine that there are two inverses for A, you can then actually show that those two inverses are the same. And I'm doing it on a very abstract level here. Okay, just from the definition, basically from this definition of what an inverse is, I'm able to make that calculation. Okay, so because this inverse is unique, I'm going to give you a quick little notation here, which is that the inverse of A is denoted. Here's the way we're going to write it, guys. We're going to write it as A to the -1 power. Okay, so the inverse of A is denoted A to the -1 power. Of course, this is if it exists. Remember, not every matrix has an inverse. This is if it exists. Then we know that it'll be unique. And so we can talk about the inverse of A. And we're just going to denote it this way. In other words, I'm not going to write B or C or anything like that. I'm going to just write A to the -1 power. Please do not write 1 over A. Okay. Don't try to write it as like a fraction. Just leave it as A to the power of -1. That's a very, very standard notation. Okay, so the application of this, I mentioned this on Tuesday, but I would like to just remind you one more time. Why do we care about inverses? That was one of the questions from a little bit ago. Well, the idea here, guys, is that if we have the linear system, you probably remember this from Tuesday as well, right? We wrote down A times X equals B. So if we have a linear system of equations, and instead of writing down A sharp, instead of that, if I chose to write it as, remember, we expressed that linear system on Tuesday as a matrix multiplication. You have a coefficient matrix in front. The X vector is a column of unknowns, yeah? And then the right-hand side vector B is just the constants that are on the right-hand side of all of the equations in your system. Yeah, so if we have that system, and if A is n by n, and A is invertible. So if, this is all starting off with a big if we have an invertible n by n coefficient matrix for a linear system, then, right, then we can solve for X very easily. Because what we can do is take this equation and just hit it, multiply it on the left of both sides of the equal sign by A inverse, right? So A inverse times A times X equals A inverse times B. Now I can only do that, if A inverse exists, right? So if the matrix A is not invertible, then what I'm showing you here cannot work. And then you have to go back to the Gaussian elimination that we explained on Tuesday, right? So, but if the matrix is invertible, I can do this, and we already know that A inverse times A, it's like canceling it out, right? It becomes just the identity matrix right there. And so then the identity matrix times X is just X. And so you actually can solve for X by using this formula. A inverse times B. This is going to be the X vector, right? So you could just solve for X in this way. We're going to do an example in a few minutes, but that's the theoretical justification for this application. It's why we care about, one of the reasons why we care about having invertible matrices. We can cancel them. It's almost like we divided by A, right? We moved it to the other side of the equation to solve for X. Exactly what we would do with numbers all the time without even thinking about it. Now we're saying that sometimes we can do it with matrices, but only if A is invertible, right? So that's actually a big deal. Now I can't go too long before we start like figuring out, well, how do we know if a matrix is invertible, and how do we find the inverse if it exists, right? That's going to be the next thing we have to talk about, right? This isn't going to be very helpful if we don't know how to find A inverse. So we have to learn a little bit about how to do that. Are there questions so far though? I know this is very theoretical. Okay, so inverses are unique. We can write them as A to the -1, right? And we know that if we take A to the -1 times A, cancels out to the identity matrix. That's just the definition. It's literally, if you come over here where we had the B originally, and if we just plug in A inverse now, it literally is the definition of the inverse of a matrix. It's just something that when you multiply it by A, it gets you right back to the identity matrix again. So you won't see me using the B's or C's anymore. I'll be using this A to the -1. That's going to be the notation for the inverse of A. Awesome. Okay, so yeah, let's get that next question going. How can we decide if A, which is n by n, is invertible? Okay, so I have a lot of questions here. So I'll call this another question. How do we know if A is invertible or not? Okay. And then as a follow-up question, if it is invertible, the question is, how do we find A inverse? So first of all, how do we know if the matrix will have an inverse? And then secondly, if it has an inverse, how do we find it? Okay, it's going to be the question. How do we find the inverse of a matrix? Okay, well, I'm going to kind of answer these together. It's like two questions together, but I'm going to first give you the answer only, I'm gonna give you the answer only for n equals 2, first of all. We're gonna start off by answering it only for n equals 2. 2 by 2 matrices. By the way, guys, again, if the matrix is not a square size, if it's not n by n, then nothing that I'm saying today is in the conversation at all, right? If the matrix is not a square size, it can't have an inverse. We can't use this application, right? We can't really get anywhere with any of this stuff. Okay, it's only for square size matrices. So for n equals 2, right? For that situation, your matrix is going to look like this, right? You're going to have 2 rows and 2 columns. There's going to be 4 numbers in the matrix, and we can just list them like this: A, B, C, and D. Okay. So I'm going to give you the answer to these questions now. Okay, so here's the first thing. A is invertible. It will have an inverse if and only if. So now I'm going to give you the condition. This is something you will want to know off the top of your head, which is that if you take A times D and you subtract B times C, it should be not 0. Okay, so A is invertible if and only if AD minus BC is not invertible. Okay, that's pretty important, guys. We will be seeing lots of 2 by 2 matrices in this class. So having that condition kind of committed to memory is a good idea. AD is just the main diagonal multiplied together, right? And BC, well, that's just the other 2 entries multiplied together, and you just have to subtract them. So for example, if A was the matrix, I don't know, 1, 2, 5, 7, right? You can just see if I calculate A times D and I subtract B times C, 7 minus 10, that's not 0. So this is invertible. That would be invertible. However, if we took another matrix, let's take A to be a different matrix. Let's just say it was 10 and 1 and 20 and 2, something like that. That's also a 2 by 2 matrix, but this time if I do A times D minus B times C, I can see that that does cancel out to 0, so this one is not invertible. Okay, so it's a pretty easy, as long as you have this equation AD minus BC in your mind, this is a pretty easy little box to apply. It's pretty easy to do that. So far so good. And of course, you're just taking my word for this right now, right? We're going to go into more details about like why that AD minus BC thing is showing up. But let me also then, before I do all of that, I want to just answer this follow-up question. So how do we find the inverse of A when it is invertible for a 2 by 2 case? So in this case, A inverse is going to be, are you ready for this? This you totally need to memorize, okay? It's 1 over AD minus BC. Now, so far, that's just a number. But notice that AD minus BC is in the bottom of a fraction. So this is obviously going to be important that it's not 0, because we don't want to divide by 0 here. But that is just a number. That is actually a scalar that now has to be multiplied onto a 2 by 2 matrix, right? Remember that the inverse of A is also an n by n matrix again. So here it would be 2 by 2. And here's what you need to memorize. The way you fill this out, you swap the diagonal numbers. So the A and the D from the original matrix, they will swap positions. The other 2 numbers stay in the same positions, but they pick up minus signs. They pick up minus signs. So this is the inverse of A. You have a D, negative B on the first row, and then negative C and A on the second row. Of course, if you want, you don't have to do this, and normally I'm not going to do this. This scalar that's out in front here can be, of course, scalar multiplied into the matrix. So I could write this as D over AD minus BC, negative B divided by AD minus BC, and then negative C divided by AD minus BC, and then A divided by AD minus BC. I'm perfectly free to just put those denominators into every single slot because it's scalar multiplication, right? How does that scalar multiplication work? You just multiply every entry of the matrix by that scalar. Okay? Question?
Sorry, this is for the first one you gave, right?
2 by 2.
Okay.
Yes, everything in blue.
For the one with the letters, right? Like A,
Yes, yes. If this is my matrix A, then that's the matrix A inverse. Actually, let's say you don't believe me. Let's say you don't believe me that this is the correct formula for the A inverse right here. Here's A inverse, here's A. How could you check that I'm giving you the right formula?
Multiply them together.
Multiply them together. Exactly, right? What's it say over here? If two matrices are inverses of each other, when I multiply, we refined it here. If we multiply a matrix with its inverse, we should get the identity matrix. Let's just check that. Let's just check that. Let's do, I'm going to check this here. I'm just going to check this. So I'm going to do, let's just do A inverse times A. I'll just do that one. I won't do them. I won't do both of them. But how does A inverse times A work? Well, A inverse, we'll write it down. It's 1 over AD minus BC times this matrix D, negative B, and then negative C and A. And we're going to multiply that by A itself, which is A and B, and on the bottom row, C and D. So this is A inverse, right? And this is A. And what we can do is just multiply this out. You can just multiply it out. I'm going to leave the scalar. I'm going to leave the scalar out in front, and I'm going to focus on multiplying out these two matrices. This is a chance to review again how we do the matrix multiplication, right? So I go across the rows of the matrix on the left, and I dot those row vectors with the column vectors of the matrix on the right. So the upper left corner, for example, right? I'm going to do D times A and then minus BC. So DA minus BC goes in the upper left corner. Need just a little more room here. If I go to the upper right corner, I dot the first row with the second column here, right? I have BD minus BD. Well, that's 0. Okay. And now if I go to the bottom row, I have to use the negative C and A and dot that with these two columns. Negative AC plus AC, that's 0. Right? And then the far bottom right corner of my matrix now, I go across the bottom row and the second column and I dot those together. Negative BC plus AD. Just doing the matrix multiplication dot product here. And guys, these two entries are both just AD minus BC. So if I throw the AD minus BC into the entries, if I do the scalar multiplication, look what I get. If I actually simplify that, I just get 1, 0, 0, 1. And that is the identity matrix. That is the identity matrix. So absolutely, that is checking that the matrix that I proposed here, which everybody should memorize, please put this in a box, highlight it. Definitely, it's very important, the formula for A inverse here. That is the correct formula. I multiplied it by the original A, and I got the identity matrix. This is only for 2 by 2. So far, I'm only answering these questions for the 2 by 2 matrices. So in a minute, I'm going to explain what we do for 3 by 3, 4 by 4, larger matrices. Okay. So far, so good? Questions at all? I hope I'm not going too fast. Just let me know. Okay. So, and this, by the way, this is all in section 2.6. So this will be over the weekend. I'll have you working on Gaussian elimination and this. That's kind of the game plan. Okay. Yeah, so for example, if you want to, you could back in your notes here, we could now write down the formula for the A inverse on this one, right? 1 over AD minus BC is actually negative 3. And then I just swap the diagonal numbers, the 1 and the 7 get swapped. and the other two numbers just pick up a sign change. So there's your inverse for A on that 2x2 example we started with. It's not necessary to put this negative 1/3 inside the matrix. You can just leave it factored out in front. Just keeps the matrix looking a little bit cleaner. Okay. Well, we have to talk about larger matrices now. Unless there's a question here. So far, so good, everybody? So far, so good. All right, so what about 3x3, 4x4, 5x5? It's definitely a good question here. Let me go back to my blue marker. I'm just trying to make my notes look nice. So what about the answer for n equals 3, 4, 5, or anything larger than that? The reality of it is that as soon as the matrix gets to be about 4x4 size or anything bigger than that, you really should go to a computer and go to MATLAB, or actually you just Google matrix calculator on the internet these days. It'll pop right up. You put in your numbers and it'll tell you the inverse, right? So most likely you're not going to see me asking you to do matrices by hand that are any larger than 3x3. Maybe if I was in a really bad mood sometime, I'd make you do a 4x4 matrix, but most of the time 2x2s and 3x3s are the best size to work with by hand. But the concept of how we do these inverses is the same for all of these sizes. Namely, it's the following. And unfortunately, guys, I cannot just give you a formula for A inverse like I did over there. In the 2x2 case, we've got these beautiful formulas, these beautiful conditions. It's great. For larger matrices, unfortunately, we actually have to go through a process to find the inverse. Okay, so for this one, I'm going to say we use elementary, something that I have not talked about yet, elementary matrices. So this is actually the game plan that we have to have in the case of these larger matrices. So let me give you a definition of what an elementary matrix is, and explain how this is related to finding inverses of matrices. By the way, this method that I'm about to explain, it also works for the 2x2 case. It's just that for the 2x2 case, we don't need it because we've got nice formulas for how to do inverses. Okay, so but this is applicable to any size. So here's the definition, guys. An elementary matrix, right? An elementary matrix. Usually I'll use some kind of an E for the notation for these, a capital E. An elementary matrix is obtained by applying one ERO. I'm going to emphasize only one ERO to the identity matrix. So for whatever that size is, n by n, if you start with the identity matrix and you do one ERO to it, anything that shows up in that manner can be thought of as an elementary matrix. So let me give you an example. We could have, here's an example of an elementary matrix. Let me call it E1. This could be an elementary matrix. 1, 0, 0, 0, 0, 1, and 0, 1, 0. So this is just a 3x3 example. Does everybody see that you could get this matrix by starting from the identity matrix, which is 3x3? You could start with your I3 right here. Does everybody see that you can do one ERO to it and get this matrix? Now we have to remember the EROs. The EROs, we learned them on Tuesday. You can permute two rows, or you can multiply a row through by a constant, or you can add a multiple of one row to another. Right? Those were the three things we learned last class. Well, this one you can see what happened. We permuted rows 2 and 3. So you could actually write that down to kind of help yourself see, well, what was the ERO that is associated with that elementary matrix? It's P23. Let me write down another example of an elementary matrix. Let's call it E2. Maybe we would do something like this, 5, 0, 0, 1. This could be a second example of an elementary matrix. Can somebody tell me what ERO did I apply to the identity matrix in order to get this matrix to show up? I multiplied row 1 by 5. That's exactly right. Okay, so these are what would be called elementary matrices. Pretty easy idea. The interesting observation, maybe I'll make this observation over here, is that these elementary matrices actually encode, let me just say this carefully. These elementary matrices actually encode the ERO that's associated with them into a matrix multiplication, right? Let me write that down. Just a little remark here, and then I'll show you what I mean, right? The elementary matrices behave like EROs. Elementary matrices, guys, they behave like EROs when applied under matrix multiplication. I'm going to show you what I mean. Again, this is all like a very long-winded answer to the question for matrices 3 by 3, 4 by 4, and 5 by 5. How do I know if it's invertible and how do I find the inverse? Let's not lose track of the big question we're trying to solve, but we're taking this little side trip into the world of elementary matrices here. Guys, so what I mean by this remark, I'm going to show it to you over here, right? If I take this matrix E1 and I multiply it by any matrix, A, B, C, D, E, F, G, H, I. If I do that, right, and you actually do this matrix multiplication, let's actually see what happens. Let's actually see what happens here. So we go across the rows here, we go down the columns here, right? That's how this works. If you do that, the first row is A plus 0 plus 0, and then B plus 0 plus 0, and then C plus 0 plus 0. Yeah? Second row is 0 plus 0 plus G, 0 plus 0 plus H, and 0 plus 0 plus I. All right? And then the third row would be 0 plus D plus 0, 0 plus E plus 0, and 0 plus F plus 0. So look what happened in going from this matrix to this matrix, right? What happened here, you notice that the second and third rows just got permuted. It's exactly the ERO that was associated with this elementary matrix in the first place. This is what my remark is saying. The elementary matrices just behave as if they are a matrix multiplication way of doing an ERO. Right, that's going to be the idea. That's the idea. Check it out on the second one. Check it out here. If I take E2 and I multiply it by, A, B, C, D, right? Let's see if it coincides with this ERO. Let's just do this matrix multiplication here again, right? 5A plus 0. 5B plus 0. Bottom row is 0 plus C and 0 plus D. Look at that. The first row of the matrix got multiplied by 5. Okay, so to go from here to here, we did in fact do this ERO. Oops, 5. Yeah, so that's the idea of what's going on there. So that's kind of intended to explain my remark by looking at these examples. You guys kind of following this? You're so quiet this morning. Okay, all right, good. A couple people smiling at me. That makes me feel better. Okay, so now I just need a little bit more work before I will really be able to answer these questions. These are the questions we're trying to answer, guys. Right here is what we're trying to answer. How do I know if a matrix is invertible, and how do I find the inverse if it is, right? For 2x2 matrices, it's all explained over there on that board. We've got formulas. We can just remember those formulas. But now we have to go through a little bit more of a process here for the larger matrices. So I'm going to make a definition that will be make this a little easier to talk about. So a matrix capital A is row equivalent. A matrix is row equivalent to another matrix capital B. Row equivalent to B, and I'm going to have a notation that I'll be using here for this, which is I'll start with A. I'll put a little arrow here with the word row on top of it, pointing towards the matrix B. So we'll be writing it that way. So A is row equivalent to B if there exist, right, elementary matrices. If there exist elementary matrices, I'm going to call them E1 and E2 and dot, dot, dot. It could be several of them, maybe all the way up to E sub K. So there's a series of elementary matrices with the following property. This, I think based on the remark, this should make total sense. You start with A, you hit it with E1 on the left, and then you hit that with E2 on the left, and you kind of keep multiplying, and you eventually get to E sub K on the left. That this should eventually take you to B. This should be equal to B. Okay. Now, guys, this is nothing more than saying that you start with A, and then you do an ERO to it, and then you do another ERO to it, and then you do another ERO. Remember, left multiplying matrix multiplication by the ERO, by the elementary matrices is like doing an ERO. So if I start with A and I do E1 to it, that's an ERO. And then E2 is another ERO, and then another ERO. And you eventually get to some other matrix, right? So we're just saying that two matrices are row equivalent if you can start with one of them and do a bunch of EROs and get to the other one. Right, that's exactly the definition here. That's basically exactly what we're saying. Okay. So now, that's just a definition, but I want to imagine with you guys for a minute that maybe I could start with the matrix A and do a bunch of EROs to it, which are now being encoded by these elementary matrices, right? I can start with A, do a bunch of EROs to it, and what if A is actually row equivalent to the identity matrix? What if this is I sub n over here? That's going to turn out to be the key point. So let me make that as a little note here. Right? So if A, this is just an if, I'm not saying it's always true. But if A was row equivalent to the identity matrix, this means I could start with the matrix A, I can do EROs as many times as I need to, and eventually get the identity matrix here. Then I want you to take a look at this, guys. What this would mean, according to my definition, is that, EK times dot, dot, dot times E2 times E1 times capital A is equal to the identity matrix. In that case, that would be the identity matrix. So if you can take A, I think we're just about getting to the answer to the blue question here, right? If I can take the if I can take my matrix A, and if I can do EROs to it and get it to become the identity matrix, then do you see that A is invertible? see, just remember, what does invertible mean again? Invertible meant that I could take A and multiply it by something and then get the identity matrix. This is what invertible means, basically. You have two matrices multiplied together gives you the identity matrix. Maybe I can help you. So what I'm claiming is that A is invertible. My question is, do you see that? Take this whole stuff with the E's here and just think of that as your B. Right? It's this whole product, whatever this thing is in parentheses, right? That's the matrix that when you multiply it by A, cancels it out. This is exactly what it means for two matrices to be inverses of each other. So A is invertible, and we can even say what the inverse is. The inverse of A will be all of that stuff that I put in the parentheses. EK times ... times E2 times E1. That's it. That's the whole story. So we have, how can we decide if an n by n matrix is invertible? Well, the answer is as long as that matrix is row equivalent to the identity matrix. In other words, as long as I can take the matrix and do EROs to it and turn it all the way into the identity matrix. On Tuesday, we talked about taking a matrix and putting it into row echelon form, right? We talked about getting this sort of triangular form to the matrix. Here, we're doing something even more strong. We're saying, no, I want to take A and do EROs to it and make it turn fully into the identity matrix itself, which is as triangular as it gets, right? It's as row echelon form as it gets, right? Everybody would probably agree that this matrix is in row echelon form, right? No question about that. So, but this is better than just row echelon form. If A can actually be converted into the identity matrix through these EROs, then the matrix is invertible, and we even have the formula for the inverse, which was the follow-up question. Okay. Now, the thing is, nobody wants to probably like memorize all of this stuff with the E's flying all over the place and writing down what they are and so on. So there is a nice, cool way to kind of remember it and have it in a visual. So I'm going to show that to you right now. Okay, it's something called the Gauss-Jordan technique. For A inverse. So this is a method for finding the inverse of A. And this works also for 2x2 matrices, but of course for 2x2 matrices, we're probably going to focus on using these formulas. But I'm going to give you a very simple process, which just has two steps to it. This is called the Gauss-Jordan method. It's the same Gauss that the Gaussian elimination we did on Tuesday is named after. And here is what we're going to do. We are going to form, step A, is we are going to form the n by 2n matrix that looks like the following. I'm going to make a matrix here, guys. I'm going to put capital A on the left side of this block that I'm going to make. And then I'm going to put the identity matrix on the right half. So we're going to do an example in just a minute to show how this works. But the idea is that we're going to build this sort of block structure of a matrix here. So your matrix is n by n. The identity matrix is n by n. And when you set them side by side, now you actually have an n by 2n block. Everybody with me? So this part here is n by n. And this part here is also n by n. So together, that makes the size of this block n rows by 2n columns. It's twice as wide as it is tall at this point. That's the first step. And that's just writing that down. And now how do we do this process? We're going to apply, step B, we're going to apply EROs. I'd like to show you how this is going to look. Right, so what's going to happen here Give yourself a little bit of room to write this down. This takes just a little bit of space. I'm gonna start with my block that I already created in step 1. And remember that every time I do an ERO, I usually like to put a little twiddle there to do my ERO with. And then I'm going to apply an ERO throughout this whole matrix, which means I'm going to apply it on both sides of the sort of center bar that's separating these two blocks. So E1, right? Remember, multiplying by E1 is just like doing an ERO. Saw examples of that here. These black matrices, E1 and E2, we multiply them onto any other matrix, and it basically does that ERO to that matrix, yeah? It's exactly what's happening. So we do that, and then we're gonna do it again. We're gonna do it again. E2, E1A, and then on the other side of my bar, I have E2 and E1. Okay? So we've applied a second ERO, and we can keep going. We can keep going. I'm going to go dot, 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 dot. And eventually, let's say we get eventually to EK times dot, dot, dot times E2 times E1 times A on the left side. And on the right side, we would just have the EK times dot, dot, dot times E2 times E1. Just want to make 100% sure nobody's confused here. Nobody's nervous about why the I sub n disappeared, are they? I have I sub n here, and you're like, well, where is it later? Well, remember, when you're multiplying by I sub n, it's like multiplying by 1. So you don't have to write it down. So there's really an E1 times IN here. But I'm just not writing the I sub n because it's like multiplying by 1. I don't need to do that. So I just apply my elementary row operations all the way along the line. Now, what do I have here on the left side? On the left side, I actually have this whole thing, which is actually the identity matrix. You're close. The identity matrix is actually on the left side. But at the very moment, you see this, guys? At the very moment that the identity matrix has shown up on the left side, right? What has shown up on the right side? Now I'm ready for it. The inverse of A, exactly. Exactly, guys, this is what ends up happening. This is what ends up happening, right? This is exactly how the Gauss-Jordan method works. Okay, so you put your matrix on the left side, the identity matrix on the right side, you hit both sides all the way across with EROs, and at the very moment that you get the identity matrix on the left side of your block, the inverse of A is going to show up on the right side of your block. It's beautiful. So you don't have to remember most of this stuff up here, right? You can kind of just let this drift into the back part of your mind and keep this two-step process up front and center. Okay. Now, you might be thinking, oh, well, wait a minute, I could do this process with any matrix. Every matrix should be invertible, right? I could start with any capital A, put it into this block, and start doing EROs on it. Well, but the problem, of course, with that is that some matrices, there will be some matrices that I don't care what clever EROs you try to use. You start with this matrix A, you start hitting it with EROs. There will be some matrices that no matter how hard you try, no matter how many EROs you try to use, you're never able to actually get the identity matrix to show up on the left side. I think there's a homework problem for next week where the matrix A has a row of zeros in it or something. I forget exactly what the numbers are here. It's a 3x3 example from the homework. I think there's a problem like that. And I tell you what, if you put that on the left half of your little block here and start doing EROs to it, this row of zeros, you will never be able to turn this into the identity matrix. No matter what EROs you try to use, it will not be possible. And so if you can't get the identity matrix to come out on the left side, then you're not gonna get the inverse of the matrix on the right side, because they have to come hand in hand. Right? So finding the A inverse here, right, is part and parcel with being able to row reduce A down to the identity matrix, which you cannot always do. Let's try an example of this Gauss-Jordan method, if everybody's okay. So far, so good? Again, you don't need all this nonsense if it's just 2 by 2. If it's just 2 by 2, we got these beautiful formulas here, and it's no sweat. But let's try a 3 by 3 matrix here. See if we can find the inverse of a 3 by 3. Okay. So here's an example. Let's try to find A inverse. I'll say if possible. We don't know if it's always possible, right? If possible, I'm going to find A inverse where capital A is going to be the matrix 1, 0, 1, and then the second row is 0, 1, 1, and then the third row is 2, 3, and 6. Okay, so let's try that. So it's a 3 by 3. We don't have a simple formula for it. So for the solution here, I'm going to attempt this Gauss-Jordan technique that we just explained, right? That's going to be the approach here. And that means that what I have to do is build my block, right? So step A, I guess I'll write it down. This is step A. Step A is I put my matrix on the left side here. So I just recopy capital A again on the left. I'm going to put a big bar in the middle. Okay. And then on the right side, I put my identity matrix, which has to have, of course, the same size as whatever the original matrix was. So I'll put my 3 by 3 identity matrix on the right side. And that is my starting point for this Gauss-Jordan technique. Okay. Now I'm going to jump right into step B. I'll put B here because we're going to go into step B immediately. I now need to apply EROs. And the objective of the EROs is to try to get the left side to turn into the identity matrix, if possible. If possible, okay? So how are we coming with that? I can see I've got a pivot here and here. It's okay to circle those like we did last time. And the first step in trying to get the identity matrix to show up on the left side is actually to just bring the matrix on the left side into row echelon form. All right, at least attempt to do that. So I'm going to try, my friends, I'm going to try to bring the left side into row echelon form. Can somebody give me a good ERO to start off with here? You remember from Tuesday, those the permuting or the multiplying or the adding. Have any ideas here? Blake, go ahead. Multiply the third row by what now? So we don't really multiply 2 rows. That's not an ERO. The EROs are, I can multiply a row by a constant, or I can add a multiple of one row to another row. Marco?
Multiply 1 by -2 and add that to row 3.
I want to turn this 2 into a 0, right? So I'm going to use a -2 multiple of the first row and add it to the third row. That sounds pretty good. So let's do A13 of -2. Okay, so let's review how that works, right? What happens is the first row actually doesn't change at all. And we're not talking about the second row either, so we'll leave that the same as well. It's the third row that feels the effect of this ERO. So I'm taking -2 times the top row, and I'm going to add it to the bottom row. So I should get 0, 3, 4, and then -2, 0, and 1. I'll go ahead and circle these pivots again. And at this point, the first column is perfect on the far left here, right? This is in good shape right here. Okay. Now I need somebody else to give me an idea for an ERO to go from there. Audrey? Same thing. Great. So I'm going to do the A operation again. A23 of -3. So where we're getting that from is just looking at these two numbers, right? The 1 and the 3 right here. I take the -3 times that middle row and I'm going to add it to the bottom row. That will not affect the top row at all. So I'll recopy the top row. Okay, and that will also not affect the second row. So I'll just recopy the second row. But -3 times the top row when or times the middle row, when I add it to the bottom row, is going to give me 0, 0, 1, and then -2, -3, and 1. Remember, this is the stuff we have to do when we're fresh. Right. Don't do it when you're tired. Don't do it late at night. Don't do it right before bed. This is not good to do when you're not feeling alert. So gotta be real careful with these EROs. Alex, you look like you want to ask me a question.
Yeah, sorry, I don't get like the step B, how you go from A to B. You're,
From here to here?
yeah, like the operation that you're doing.
Yeah, A13 of -2. So what I did is I took -2 times all of these numbers in my head, and I added them to the third row.
Oh, okay,
So like -2 times 1, I added that to 2, it became 0.
okay.
Right? -2 times 0, I added that to 3, it stays as 3, and so on. Okay, so these are my EROs. Yes,
No,
Adrian,
the one on the set of matrices on the right side of
of the bar? Yeah.
Yeah, we don't have to put those in there.
No, we're mostly focusing on what do we need to do on the left side in order to get the identity matrix to show up. And we have to do these EROs across the entire matrix. So the right-hand side is just along for the ride. Whatever EROs are happening, it gets affected by them, but it isn't really driving our decisions on the EROs. Yeah, good point. Really good point. Now, guys, if this was Tuesday and I just said, what's the row echelon form of the matrix on the left, we would have just said, here it is, and we could have stopped because this is in row echelon form. But today, we're trying to do even better than that. We're trying to get the identity matrix to show up on the left side. So I am actually not done yet. Yes, Eduardo?
Oh, it's just,
You're going to tell me the next
Yeah.
step to do? Excuse me, I need to get rid of these ones, right? They need to become zeros. What would you like me to try?
I was thinking if you can multiply the last row by -1 and add that to the second row.
Okay, exactly. We can take the negative of row. Now, you didn't see me do this a lot on Tuesday, taking a lower row and some multiple of that being applied to a higher row. That's exactly right. I want to turn this 1 into a 0. And so, guys, don't recopy the first row yet because I'm going to do something with that in just a second. The third row stays the same. And we're taking, Eduardo's idea is to take the negative of that third row and add it back to the middle row. So that'll give me 0, 1, and 0. So again, the negative of the third row added back to the middle row makes the middle row turn into a 2, 4, 1. So everybody see what happened? I took the negatives of these numbers and added them to these numbers. Okay?
Or negative?
2, 4, oh yeah. Yep. See, even I can't be a zombie either, or I'll mess it up.
So we're trying, after we put in X1, put it in.
We're trying to get it to become exactly the identity matrix.
Okay, isn't that-
There's something called reduced row echelon,
Yeah.
or didn't really talk about that too much because it's not really that important.
Oh,
But yeah, that is technically what it will be. Yeah.
Okay.
Mhm. Yeah. Can I do anything else at the same time just to save a little writing? Go ahead, Jerry.
You can also do the same thing for row 1.
Okay, great. So what would be the operation?
Be adding row 3 to row 1 by -1.
Beautiful. Exactly. I can also take the negative of the bottom row and add it to the top row. It's exactly what I would like to do. So I'll get a 1, 0, and 0 now. And again, I'm taking the negative of the top row, the negative of the bottom row, and I'm adding it to the top row. And so that should be all we have to do because I have I3 on the left side. And the minute that the identity matrix shows up on the left side, my inverse of my original matrix shows up on the right side. So that's how this works. This is A inverse right here. That is A inverse. Is it clear how this Gauss-Jordan technique works? It's mostly just a lot of EROs, just to not sugarcoat it. That's basically what we have to think about. Yeah, question.
So this is not.
Well, if you are unable to get the matrix on the left to become the identity matrix, then you have no chance. So let's say, for example, that this had been all zeros here. And you start doing EROs, permuting two rows or multiplying a row by a constant or adding a multiple of another row. These three zeros are sort of stuck in concrete. They're never going to change. And so you'll never be able to get this identity matrix. You won't be able to get that one right there. And so if you can never get to the identity matrix on the left, then that means that you're not going to ever get to an inverse on the right.
So it would just be like, because there's not an inverse for every.
Right, not every matrix has I mean, imagine what would happen if your matrix, what if A was this matrix? Right? I mean, imagine trying to do EROs on this, okay? Permute two rows, multiply by a constant, whatever. Nothing's ever going to happen, right? You're never going to be able to progress towards the identity matrix on the left side for something like this. Or even for something like this with a column of zeros in it. And there's other scenarios that don't work as well. Even this one. 10, 1, and 22. If you do the Gauss-Jordan technique on that, you'll never be able to get 1, 0, 0, 1 on the left side. This one simply won't work. Okay, so I know we're still thinking a little bit about how do we know like if a matrix has an inverse or not. I promise I'm gonna make this even more transparent for you as we go forward. Okay, so we'll come to that. I want to do one more thing though before we take our break today, which is a follow-up to this problem. Let me just give you one more example here. So let's make sure this was correct. This was a 1 actually and a 2. Okay, so let me do one last example before we take a 10-minute break. And here's the example. Let's solve x plus z equals 7 and y plus z equals -1 and 2x plus 3y plus 6z equals 2. This is a system of equations. I would like to try to solve this system of equations. Now, on Tuesday, of course, we learned how to do this. We basically put this matrix into an augmented A-sharp thing where we, all the coefficients go on the left and we augment it with these numbers on the right. And we do EROs and get it into a row echelon form, right? And then we solve it by back substitution, right? We saw on Tuesday that could involve free variables, or maybe it's if the pivot goes to the far right column, that's not possible, stuff like that. I would like to show you though, that there is a different way that we can actually solve this problem. Because do you notice anything about this system, the coefficients of the system here? It's the same as the matrix A here, right? Which we just said was invertible and we just found the inverse. So if you want, what you can do is you can recognize here, guys, that this is actually nothing more than A times X equals B. It literally can be written as a linear system this way, where the A is exactly the matrix that we just worked on, 1, 0, 1, 0, 1, 1, 2, 3, 6. And remember how we showed on Tuesday that we can put our unknowns into a column vector that we're going to multiply by on the right. So that's X, Y, and Z. Those are the unknowns. And the other side of the equation has the values on the right-hand side of all of those equal signs, right? So this is just rewriting our system in kind of a matrix multiplication style. And the goal is to solve for X, Y, and Z, right? Of course, that's what we're hoping to do here. So instead of doing A sharp and doing all the EROs to that, we have a much faster way to get the answer now. So let's just recall that if we have A times X equals B, that we can actually solve for X by using A inverse. So the X will just be A inverse times B. Remember, this was the application that I had mentioned just a little bit ago. So we can just take the A inverse and multiply it by B. And of course, that is only, this only works, right? This only works if A is invertible. This only works if A is invertible, but on the problem that we just worked out, we've already seen that A is invertible, and we even have the inverse right here. So if I want to know what X, Y, and Z are, X, Y, Z, it's just going to be equal to the inverse of A, which was 3, 3, -1, and then 2, 4, -1, and then -2, -3, 1, and that gets multiplied by B, which is 7, -1, and 2. We're just going to multiply. In a second, we'll just do our dot product multiplications to come up with the answer here. Okay, so this is A inverse times B. And let's just do that calculation. Okay, so I'll go across the rows of A inverse and I go down the columns of the vector B here. So the first entry is going to be 21 minus 3 minus 2. 21 minus 3 minus 2, which is 16. Okay, the second row, when I do that dot product, I have 14 minus 4 and then minus 2. 14 minus 4 minus 2 is just 8. And finally, the bottom row is -14 plus 3 plus 2, and that should add up to -9. And so that is my solution. We could write it in our fancy braces notation like we did last time. X, Y, and Z just get listed as a triple of numbers in parentheses right here, right? So X is 16, Y is 8, and Z is 9. You can check it, right? X is 16, Z is -9. Yep, that adds up to 7, right? Y plus Z adds up to -1, and so on, right? All of those equations are going to work. So this is kind of nice, for example, if you were out in the real world and you solved this problem and then suddenly you realize, oh, wait a minute, I need to solve it again with different values over here. The 7, -1, and 2. So if you change those numbers, you don't necessarily have to start over again. You can just take the same A inverse and just edit these numbers and then do the calculation again, and voila, you've got another answer to another problem. So it's nice if you have this inverse, you only have to calculate it once, right? And then you can take this same left-hand side and mess around with these numbers all you want, and in the snap of a fingers, have another answer for another linear system. So, right. If A was not invertible, then you would not have been able to do this, of course. So if the coefficient matrix is not invertible and you wanted to solve this system, then you're back to Tuesday's stuff. Then you got to do the augmented matrix, do EROs. Potentially you'll have free variables in that case, right? Here we didn't have any free variables, but you might have free variables in that case, which you could introduce and then write down the general solution. So that's you can always fall back on the Gaussian elimination that we did on Tuesday. And in fact, if the coefficient matrix is not a square size, then it's pretty much game over before you even start. You have to do Gaussian elimination, right? There's not going to be an inverse for a matrix if it's not square size. So, okay. Really good. I have just a little more to kind of tie this all together. I'm going to do it after we take a break, though. Let's take 10 minutes and get some fresh air. Stretch your legs if you need to. The balcony at the end of the building might actually be comfortable to stand out there today, if you want to go do that, unlike most of the rest of last week. We'll start up again in 10 minutes. And if you have anything else to add to the homework list, feel free to do that during the break as well.
We were doing it with all like letters over here.
Mhm.
It's very popular.
Uh-huh.
So this is the.
Yes, this is the inverse that we just found right here.
Oh, okay, so we just use.
Just using
Yeah.
that, and then I'm just multiplying that by the p back through here.
Okay, because I was looking at this one.
Uh-huh.
And we go from.
Oh, yeah, it's just, we're taking the A, now over here we have the A inverse. Solid.
But it's the same numbers, right?
It's the same numbers. This was literally a follow-up problem to this one.
Yeah.
We already did this work, so
I thought
oh,
this was like a new setup because.
Oh, no, the numbers are, these numbers here are exactly, I did this on purpose, right, to make all the.
Okay.
Very good. Oh. We were in time.
Just see this is like red oranges. It's my lane, it's just like. So he hit me. But it was like, yeah, like sort of the way I was hitting it. And the demo. I have 2 more songs. Maybe 42.
What'd you do?
Like, it was like sitting there, the string there, like, that guy. Great friends. Not very, I mean, just not really, that was just a scratch, it was like a thing that scratched, but I didn't work, it's like, it's just not too low, that it's just one, 2 grams, like. That's literally what it is. But her car was. Door was basically. I was trying to get more from the.
But I kept like in my mind, I was like, so I'm like going along Congo. I just kept thinking, like, I kept thinking, it's a little thing, you know, but it's not really. I don't know, I just know that she's going to
I'm thinking, I was just going in rows and moving. Trying to find it. I thought I guess when I'm reaching.
I was reading, I should just like, I was like, I'm reading. Did you ever watch the? Oh, yeah. But. Oh, what's it called? Not the worst thing. I was just. Oh, there was a church.
He's that's right. Because I went into it. I wasn't the house. I'm just trying to find out what shit. Then she started. So people since it's like try is a lot, so it's trying to do. But then I tried to call them. You know, also and do that. That's kids stuff. That's never the reason why I felt like I'm consciously ready to think. Like, yes, Jack, back there.
Then they get myself what to do. And.
That's why I should have. I should have started with Warner insurance. That's still, let's say two, but I think I might just switch it to be. Yeah.
And I found that it was pretty slight. That's the rest of it. I started running videos on. Set up the, well, you guys basis, which you also make. As this, we're already like, 2 weeks this should operate. Yeah. Like already, every morning when it's up to 4 o'clock. I realized that squeeze wide enough, but what? The line passes from.
I didn't test drive a single thing.
Or 6:45. Yeah, we have no praise. Huh? Yeah, the gaps. No, so I always think that is not a week. It's basically 12 to 30. That's my days. 12 to 2:30. Yeah, and then I have like straight after that. We started up all the last 2 days, which was not one. Very much. What? I think I'm very fast. They give me three, like 2 lessons that are just week, 2 weeks, 2 weeks months of time. We're talking about now I'm gonna have, I don't know. I don't really know. See the free.
Even like I did that.
Which one was a 3-1? Just I kept going around and it's okay. But it's like this is super easy. Okay.
Yeah, well, the two of them, Tell me, is that what it's
You're gonna start now? You guys downstairs? Yeah.
Starbucks.
I was gonna start yesterday and I was looking over them and I was having a moment yesterday. And I was looking over it and I was like, you know what? I can relax now and I can do this tomorrow. We have dynamics for tomorrow. Yeah. I haven't started.
Everybody, I think, most folks should be back by now, and I might go ahead and get started again so that we can kind of finish everything up we need to do here. Did anybody have any questions about what we talked about the first half of the class today? The idea about finding an inverse for a matrix? This Gauss-Jordan technique is really your ticket for how to do it, right? It's basically the ticket. You put your matrix on the left, put the identity matrix on the right, try to do EROs to it and see if you can get the identity matrix on the left side, because if you do, then the right-hand side will have A inverse on it. I think what I'd like to do for a moment, to wrap up chapter 2, really, other than some homework and some group work that we're going to be doing, I'd like to write down, and this is actually in section 2.8, this is the very end of chapter 2. I'm going to write down something called the invertible matrix theorem. And this will help us with, it's somewhat theoretical, as you could kind of tell today, guys, that what we were talking about was a fairly theoretical topic. So I'm hoping that this will kind of help summarize it for you. Hopefully it'll make sense. Okay. So this goes under the name invertible matrix theorem. There's actually no homework for you to do in this section. This is only 2 pages long, and it's really just a brief sort of summary of some of the theoretical stuff that we were just talking about. So here is what this invertible matrix theorem says, guys. Let A be equal to an n by n matrix. So we're going to take a square matrix. Let's call that capital A again. And then what I'm going to write here is the following are equivalent. The following are equivalent. What that means is when I say the following are equivalent, I'm going to make a list right now, a list of statements. And what it means when it says the following are equivalent is that all of the statements that I'm about to write down are either true about a matrix or they're all false about a matrix. So let me show you what I mean. The first statement here, statement A, is capital A is invertible. Capital A is invertible. And again, just remember over here, I'll just remind you that just means that there exists an A inverse, right? A to the minus 1 with A times A inverse equals the identity matrix, which is equal to A inverse times A. So that's just what it means. I'm just kind of reminding you that an invertible matrix is one where there's an A inverse that exists, and A times A inverse should cancel out to the identity. Okay, so now what I'm going to do though is I'm going to start making some additional statements. And so remember what I said, these statements are either all true about a particular matrix or they're all false. So if A is invertible, then everything else I'm about to write down is true about A. If A is not invertible, then everything else I'm about to write down is not true about A. Okay, so here is another point. The equation, item B, the equation A times X equals B has a unique solution for X. So that remember that when you have a linear system, It could have 0 solutions. It could have 1 solution. It could have infinitely many solutions. We saw all 3 of those cases on Tuesday. But if A is invertible, then I guarantee you that your linear system has a unique solution. And in fact, we already know what it is. We already know what it is. I'll put it over here, right? We already know what it is. X is A inverse times B. It's exactly what we just did on this last warm-up, or this last example before we took the break. Here was a linear system. And because A was invertible, right? This capital A was invertible, we came up with one unique solution for X. There was one solution. There's no free variables, but it has one unique solution. Okay, so that's kind of consistent with that. The third point is related to it. If we look at the equation, item C, if we look at the equation A times X equals 0, this also would have a unique solution because it's, the B value here is 0. But in this case, it has only the trivial solution. When I say trivial solution, I just mean X equals 0. So if it's the system AX equals 0, then it just has the unique solution X equals 0. Okay. The next one in my list, I would like to talk about the rank of the matrix. You guys remember what the definition of the rank of a matrix is?
How many?
Pivots. How many pivots in the row echelon form? Exactly. Does anybody have an idea for an invertible matrix, what the rank is going to be? If it's an n by n invertible matrix, it's going to be n. How do I know that? Well, I know that because the row echelon form of A, we're going to write this down. The row echelon form of A, my friends, if A is invertible and you do EROs to it, you can actually use the identity matrix as your row echelon form. And how many pivots does the identity matrix have? Well, definitely n, right? They just go all the way down the main diagonal of the matrix. Okay, so an invertible matrix always has full rank, right? As big as the n from the matrix, right? So a matrix of full rank is always invertible. Okay, a couple more things here. Part E, A can be expressed as a product of elementary matrices. So I've erased that from the board. Well, not really. I've kind of still got it here. The A is basically the inverse of these elementary matrices, which are being multiplied together. And so the A itself would also be expressed this way. This is not such a useful one. Like, it's very rare that you're going to be handed a matrix and anybody's going to ask you, oh, could you please write it as a product of elementary matrices? That's not probably what you're going to get, because that's just a lot of work that doesn't really give you anything that you want. So item E, we won't talk too much about right now. The last one, this one is pretty, I think, self-explanatory. If A is invertible, then it will be row equivalent to the identity matrix, right? You will be able, for an invertible matrix, you will be able to take A and do EROs successfully and get it to become the identity matrix. That's what that means, right? A is row equivalent to the identity matrix. Okay, clear enough? So if somebody hands you a matrix, right, such as, the matrix A that we used here on that last example, if somebody hands you this matrix, right, that matrix will either be invertible or it will not be invertible. And the point is that if it's invertible, all of these things will be true about it. You'll be able to row reduce it to the identity. It'll have full rank. If there's a linear system of equations, there'll be a unique solution, right? All of those things are true if A is invertible, like in this example, right? This matrix is invertible and all of these things are true. There was a unique solution to our linear system. The matrix had full rank. It was a rank of 3. We were able to row reduce it to the identity. All of those things were true about that matrix. Okay. On the other hand, if the matrix that somebody hands you is not invertible, well, then all of these things are gonna fail. It won't have full rank. You won't be able to reduce it to the identity matrix. The Gauss-Jordan technique won't work, right? And none of these things will work out well. Okay, so that's basically what we're saying. This is a list that we have started here, but I have to tell you, there's nothing in this list that is terribly friendly. If I just hand you this matrix and you're like, I wonder if it's invertible. The only way to figure it out, at least so far, is, well, I got to go ahead and do a bunch of EROs and see if I can get it to work out. See if I can get it to become the identity. It's kind of tedious, right? Who wants to do all of that work? So this is a start to a list, but it's not a great list. In the back of the book, the back flap of our book, the very end of the book, there is an entire list of the invertible matrix theorem. And by the end of the semester, we will be adding G, H, I, ... We're going to get all the way down. The theorem goes all the way down to S. We're going to get somewhere around P. We're going to be adding things to this list. This is as far as we can go for this moment. We're going to be adding some things to this list. And hopefully there'll be some things in the list that are still to come that'll be a little more user-friendly than things like, gee, I can express the matrix as a product of elementary matrices, right? Wouldn't it be nice if we could just take our matrix A and calculate some number with it? And if that number was something, then we would say, yeah, it's invertible, or nope, it's not invertible. I mean, we've got that already for 2 by 2, right? A, B, C, D. If it's 2 by 2, all we do, remember from this morning, we just check if AD minus BC is 0 or not. That's so nice, right? So before you go to the headache of a whole series of EROs, wouldn't it be nice to just take your matrix, find a number to associate with it, and if that number is 0 or not, that will tell me whether the matrix even has an inverse or not. It turns out we're going to do that. We are going to do that. In fact, we're going to spend all of next week talking about it. I'm going to add it to the list right now, though. I'm going to put something here that we have not talked about yet. But this is a big deal. This is statement G. And so just write it down with me for now. I promise you in the next few days, you're going to totally know what this is about. DET, the determinant of A. DET of A, as long as that number is not 0. As long as that number is not 0, then the matrix will be invertible. See, I'd like to know whether I'm going to have an inverse before I start, doing a tug of war with EROs. Right? I don't want to take my matrix and have to start doing a whole bunch of heavy work. Those EROs are kind of tedious. Before I launch into doing that, wouldn't it be nice to check just a number and see if it's 0 or not? And if it's, as long as it's not 0, then at least I know I'll succeed in being able to find my A inverse. I would hate to not know if my matrix is invertible, and then I'm just going endlessly trying to get this thing row reduced to the identity. And if I can't do it, I'm like, well, okay, well, I just put a lot of time into something that didn't work. Right? It's kind of frustrating. You wouldn't want to do that. Okay, so we're going to talk about this determinant idea a lot next week. I'm not going to have much time for it today. Maybe I'll have a couple minutes. We'll see how the time goes. But this is a good, from a theoretical perspective, this is a good thing to be kind of digesting, right? Be thinking about it. All of these things come together as a package. They're all true or they're all false for any given matrix. Okay, fantastic. That's, for the most part, that's it for chapter 2. I do want to mention a couple of these homework problems here. So let's turn our attention. This is for tonight's homework. There were a couple of questions that got onto the sideboard over here. Let me talk about this 32 because a lot of people do tend to ask me this particular one. It's asking us to show something. This is on the homework that's due tonight. It's asking us to show that if we have a square matrix that is both symmetric and upper triangular, that it is a diagonal matrix. So this goes back to that 7-minute video that you guys watched last weekend about special matrices. I wonder if I can find it really quick and put it up on the screen for you. Just to show you again, let me find this thing. I'll just go ahead and see if I can get that screen. So it might take a minute. There we go. Okay, so see in this handout, I talk about symmetric matrices, and I also talk about upper triangular. So this question is saying, well, if you have a matrix that is both symmetric and upper triangular, then why does it actually have to be a diagonal matrix? Remember, the diagonal matrix has all zeros except maybe you have some numbers on the main diagonal other than 0. Okay, so these are just examples over here. When you're writing up number 32, you should not just show an example because, if I tell you all Saturdays are sunny, and then I take you outside this Saturday and it's sunny, that's not going to convince anybody that all Saturdays will be sunny. That's just like one example of that statement. So we can't just do examples, but this just kind of helps, I think, with the intuition a little bit. So let me give you what would be a decent write-up over here. You can write this down. Just put it into your homework. What I would probably do is say something like this. I would probably say, since A is upper triangular, so if you look at the upper triangular form there, which is item 3, you see that all of the entries below the main diagonal are 0. The southwest corner of that matrix, they're all 0. So all entries, just write this as a paragraph, guys. All entries below the main diagonal are 0. Those are all 0. But since the matrix is also symmetric, remember that if it's symmetric, then whatever's going on, right? Whatever's going on in the northeast corner of the matrix is just a mirror reflection of what's going on in the southwest corner of the matrix. So since A is symmetric, we conclude that all entries above the main diagonal, since A is symmetric, we conclude that all entries above the main diagonal are also 0. Because whatever happens below the diagonal would be the same as what's happening above the diagonal in a symmetric. Right. Okay, well, gosh, that means that most of the matrix is 0. Everything above the diagonal, everything below the diagonal, it's all 0. This is the definition of a diagonal matrix. A diagonal matrix is one that is both upper and lower triangular. It's got zeros both above and below the main diagonal. So this is the definition of a diagonal matrix. Okay, so you're just explaining this one in words. So if you jot that down, feel free to, if some of you want to write it up later, you can always take a picture of it. Just finish this on your own time later on. But something like that would be perfect. It's just a quick paragraph. It's a quick paragraph. Just a few lines. Does that make sense? The reason I assigned this one is just to kind of get everybody thinking about these special matrices one more time. Yeah. Okay. So that's the reason for that. Okay, perfect. So that's number 32 in section 2.1. The other one that was on the sideboard over here is number 4 from section 2.3. Let me myself a little room here. This one is really quick. They give you this expression here, with 4 slots in it. There's an S minus 2t, 2s plus 3t, and t. And I want you to just imagine like those are the positions of these unknowns, right? So we have 4 unknowns, which are labeled as such, x1 through x4. And they're just asking you to verify, right? They're asking you to verify that 4 tuple, those 4 values for x1, x2, x3, x4, that they really do solve your system. So the system has several equations. You need to check each of them. And when I say check each of them, what I mean is just plug in these expressions. So x1 was s, s2 was s minus 2t, and then we have minus x3, which is 2s plus 3t, and then plus 5 times x4, which was t. They just want you to check what that equals. Okay, so if you just check it out, you can see that the s's cancel and all of the t's cancel, and it does actually equal 0. You can just put a little check mark next to that, so it confirms that it equals 0, which is what it's supposed to equal here. Okay, and I just need you to do that. I'm not going to do the others. You guys can check I think there's 3 equations in total for that. This is the first one. So this dot part I'll leave for you guys to do, but it's basically the same thing again. That look okay? All right. Let me just see. Yeah, okay. So what I could do, there's also 3i is listed over here. So I think that's the one. I'm not gonna do this one really. I'm just gonna say a quick word on it. 2.23i. So 2.23i, what they have there is they ask you to find A transpose times A, and they give you the matrix A. So let me write it down. A is the matrix 1, -1, 2, and then on the second row it's 3, 1, 4. And they're asking you to figure out what A transpose times A is. So the transpose, remember when you do A transpose, you have to swap the rows with the columns. So that first row becomes the first column. So that's A transpose. And now you're multiplying that by A. So just recopy A right here. And so the size of A transpose would be what? What's the size of this first matrix? 3 by 2, right? And what about A itself? This one's 2 by 3. So the first question is it even legitimate to do the multiplication? As long as these two numbers match up, right? As long as those are equal, then we get a legitimate multiplication that we can do. What will be the size of this resulting answer? Anybody remember? 3 by 3, exactly. So this is going to be 3 by 3. And the way we fill out these numbers is we just do dot products, right? So we go across the rows and of the first matrix and down the columns of the second matrix, and we just do dot products. So like on the first one, 1, 3 dotted with 1, 3, well, that's 1 plus 9, which adds up to 10. Okay. And then for the 1, 2 entry, we would take 1 and 3 and dot that with -1 and 1. So that's -1 plus 3, that's 2. Okay, I'm going to let you finish it from there. That's basically how you do it. So this is one that you can also calculate. Should take you 1 minute at the most. Okay. This is a pretty short assignment. I will have office hours later today if you have questions on it. I'm going to do something unheard of, which is I'm going to stop like 2 minutes early. I rarely do that. On Tuesday, we might do a little group work to review some of the stuff from this week, but next week it's all about chapter 3. That'll be mainly what we're going to talk about. So, all right, that's all I got for today, folks. Work hard on this homework for Tuesday, guys. Perfect. Do not wait until Monday night to start working on Tuesday's work. This is going to take quite a bit longer than the assignment that you're given for today. So get an early start on this. Thank you.
No, it's all on the solid to be.
You know, it's probably game over for bro.
Over, you're gonna need to work. That was a.
I had to dash down to 5 minutes.